Hello, everybody. Welcome. Good evening. A great pleasure to me today to present Xavier De Kestelier. Xavier is a good and old friend. He's the head of Hustle Design Studio in UK, in London. But he has been for many years a co-head of the research and development team at the Forsters and Partners, which is actually when we met. And I was telling him that when he first came to a lecture at IAAC, Xavier is a pioneer in digital fabrication, a pioneer in parametric architecture, a pioneer in landing into practice much of the work that you are exploring here, we as an institution explore, but also what became or came to become a kind of much more mainstream. No? But at that moment, that was a very pioneer work. So he was actually leading it, not only in research and in explorative environments, such as the smart geometry, which was a foundation that was gathering experts from all over the world to create this kind of massive, huge workshops for a week intensive experience. But he was also landing it in practice, no? So the first time that he came to lecture, he started his lecture by showing us a yacht. No, and I said, wait a minute, Xavier, I mean, do you really do architecture? What is happening here? But I think it's interesting, no, because especially for digital fabrication, one of the first, let's say, industries that they have worked with this idea of mass customization and what you get to know in the beginning as a contouring is the SIP industry. So, you know, like there was a huge potential there on learning. And of course, it's not only yachts that Xavier has been working on. He was in different projects involved when he was at Forsters and Partners, such as the Apple headquarters and different airports around the world. And he has one more obsession, which we find extremely interesting from our side, that is the obsession of figuring out how new technologies, digital technologies, could be applied for solutions and construction in extreme environments, which is a bit what he's going to be showing us today. But his main obsession is basically with extraterrestrial environments. So we're going to be also seeing work that is in space. And of course, work of additive manufacturing in different places in the planet, but in extreme environments. I'm not going to say much more about his work or his project, just to say that Xavier is also a very close collaborator of IAAC. He has been a faculty at the MA CAD program, and he's a very frequent create in different programs. Tomorrow he will be joining us for the 3D printing architecture final presentation. And he's also working with us in some very crazy explorative projects that you will hopefully get to know soon. So no more to add from my side.
Okay, fantastic. Thank you. Let's get started. Well, thanks again for having me here. Third time I'm here. Hopefully I'm showing some different type of work. So I'm going to talk about additive manufacturing, 3D printing in extreme environments, because that's a little bit of a kind of a, you know, I'm going to see some of that work here in IAAC as well, hopefully tomorrow. And it's a little bit of a thread through my work as well. So first of all, a little bit of background. I'm at the moment the head of innovation and one of the heads of design at Hassel Studio. We're quite a large practice. We are about 800 people spread around the world in offices in Australia, in China, in Singapore, in London, and also now we have an office in San Francisco. As you see, this is kind of the type of work we do, quite a variety of work, different types of typologies, from museums to visitor centers to cruise terminals to big master plans and workplaces. But how do I fit in that role? Well, I have a tiny team. It's really fun. A tiny team of really specialized architects. We're based in London, and we are the innovation team. And the way we do innovation is really through projects. So it's not only just that technology, software and hardware. Of course we do, but we always want to apply it straight away, right? And today I'm going to talk about a few projects. So I'll talk about technology, but really through projects. It's 4 projects we're going to talk about. Right? One of them is on Mars, is a 3D printed habitat we did for NASA. The second one is actually a workshop we did here in Madrid at the Norman Foster Foundation. The third one is a 3D printed pod, meeting pod in Senegal and Switzerland. And the fourth one is an art and music center in Uganda, which is in Bidi, northern Uganda, the second largest refugee settlement in the world. So you see, we kind of get around to different places. And hopefully there's a kind of the same way of thinking about design in all these projects. First of all, I have to say, I was here about in 2010, where with smart geometry. That's right here where we're sitting. Fantastic to have this picture now. And it was at one of these conferences. It was not at this one. It was at an earlier one that we did in Waterloo in Canada, where I first came across 3D printing. And that was, I think, 2004, where I saw this machine for the first time in my life. I was completely amazed by it. I was like, wow, what is this? And particularly then at Smart Geometry, where we kind of really messing about with the first parametric modeling tools like generative components. And then we straight away could then 3D print some of those, which was really like magic, right? I just had it in a computer and suddenly it could come out of a machine layer by layer. For me, it was just magic. But immediately when you know, as an architect, when you see this machine going back and forward back then, I was thinking, like, can we scale it up? How are we going to do this? Who is thinking about that, of actually making real buildings out of this technique? And for me, it all started by, okay, and at that point, I got really excited, got back to the office as well. And of course, we started to buy our first 3D printers at Foster's back then. But for me, then kind of scaling it up to building scale really happened when I met this guy in the corner there on the right-hand side here, which is Rupert Soar. Dr. Rupert Soar from back then, Loughborough University. We met him at a conference, and he was really interested in termite mounds and how termite mounds really operated, really from a building perspective, of a building control perspective, how they kind of environmentally worked, these termite mounds. And he's way better into explaining this than I am, so I'm not going to even try. But the issue with it was, at that point, is that nobody really scanned the inside of a termite mound. And the most thing people did was just kind of like taking a hacksaw and taking cuts out of it and making an idea of what it might look like. So Rupert went to Namibia and did the following. He wanted to create a scan of these termite mounds. And the best way to do it, he thought, was by actually pouring plaster into it. Right? And you see these kind of amazing structures appearing. What he really wanted to do is also scan them, actually have a 3D scan of them. The best way at that point to do it was the following. They covered the whole termite mound with plaster, inside and outside. This is in Namibia. They built this massive structure. They had some funding, but this massive structure kind of really is built by, not roboticists, it's built by construction engineers, like a building almost around it. And then they had this grinder. And what they did, they actually grinded off centimeter by centimeter this whole termite mound. And then they had this image each time, and they took a picture of it, right? So you could really see what kind of layer by layer this termite mound looked like. That was great for their research. They did some analysis through that. And then they brought this machine back to the UK. And then Rupert had this kind of genius idea to say, like, well, actually, what if we do the opposite, right? We have this machine that can do some layered by layered process. Well, why don't we let it print something? And that was probably the first concrete printing project. It was a collaboration between Loughborough, University Foster and Partners, Bureau Habot, a few other partners. And we had the first generation machine, which was on the left-hand side, and the right-hand side, of course, is then the second generation, where they just bought a robot. But this was around 2009, right? Printing concrete. That was my first kind of, opening up to this idea of printing something, a real scale. And we were able to kind of do some crazy shapes, do some weird walls, and and I was able to get some decent detail out of it as well. It was kind of okay. I did some panels and all that, but we did think at that point as well, and a bit later as well, what is the real value of it? Because we're using a lot of concrete here. And the issue was also, concrete walls and concrete structures, they're not just concrete, right? They often have rebars in. So how do you fit rebar and steel structures within this kind of layered process? So that was actually quite a tricky thing to solve, and we didn't really solve it, I think, at that point. So I always questioned, large scale 3D printing. I was actually quite critical about it myself. Like, what is the real advantage, especially when you use just kind of masses of amount of concrete, which is not the most sustainable thing. Until I started working on this project, and here it kind of made sense. This is a Mars habitat that we did for NASA Centennial Challenge. It was a competition we did about 3-4 years ago now. And it was this competition that NASA put out, and the question was, how would you design us a 3D printed Mars habitat? It's an interesting question, especially if you, as an architect, you want to look at precedents and space habitats. There are not too many. The main one now at the moment is the ISS. There's some new ones in the making, but the ISS is the one we all look at. Now, it's not a great space to live, I would say. As you can see, there's very few architects involved in designing the space, and it's really designed by engineers. And as a human, as a habitat here, you're just a kind of a part of a big machine, right? So I think we can do much better, and I think we shouldn't actually use the ISS as an example always. You might think, well, for inspiration, I might look at sci-fi. Right, there's some really beautiful examples of sci-fi, but I'm always a little bit careful about as well getting inspired by sci-fi, because in the end of the day, these are set to tell a narrative. I'm a big fan of sci-fi, but I'm always careful to get inspired by it, because quite often these spaces look quite spacey, look quite white, they're not always the spaces I would want to live in, to be honest. So who do I get inspired? Who do I look up to? Well, there are actually a few designers that have worked in space. Skalina Balachova, she is the only female architect, well, and also the only architect working in the Soviet era for the Soviet Space Agency. She was an architect, and she worked on quite a few projects. And she made these fantastic drawings, I think. That suddenly give a completely different view of what it could be like living in space. Now, this is a module. This is, I think, one of the orbital Soyuz modules. And I just love the fact there is a little curtain. There are some wood veneers. So it's a complete different way to looking at space and these kind of really normally technically obsessed spaces to make them a bit more homey, even. She actually worked on Mir, the kind of the station before the ISS, and these are some of her drawings. I just love her drawings, to be honest. But she was not the only one. This is Raymond Loewy, famous industrial designer, American industrial designer, and he was brought in by NASA when they developed their first really orbital station. This is the Skylab, developed just after the Apollo missions. It was actually built on some of the Apollo architecture as well. And when Skylab was developed, they actually brought in Raymond Loewy as a designer. And what happened is these NASA engineers were a little bit skeptical, because they were like, what is this designer going to do in this, this is literally rocket science. Yeah, this is just not for design. What is he going to do? Like choose the color? He did choose the color. He did do that, but he chose a few other things. And two of the things you see here, he designed the table. And you might think, oh yeah, cool table. What's so special about that? Well, what is really special about it is that the fact there is a table, because originally in the design, the engineers were just having these little flaps, these little tablets. They were just coming from the wall of the space station. So the astronauts would not even face each other. So they were just facing the wall and having a meal by themselves, not even having a conversation of how their day was. That was the first thing. They needed a designer to actually decide it would be a good idea for these astronauts to face each other while having a meal. Second thing is the window. I was like, wow, okay, it's a window. What's the special? The window is round. Well, before Raymond came on board, there was no window. Imagine this, being in space for weeks and never being able to look out to Earth. So it actually took a while. It took quite a while for Raymond Loewy to convince them to have a window. Because from a pure engineer perspective, it's actually a risk, right? It's a weakness in the structure, so why have it? They can have a camera and look outside. Not necessary. But, it became the most enjoyable place for the astronauts to hang out and look back on the Earth, right? So imagine not having that view for weeks when you're going around the Earth. So designing for Mars, how do you do that? Well, one of the first things to do is really look at the environment, right? So as architects, we often do that. They're just a little bit more extremer on Mars, of course. First of all, the distance. This is the distance between Earth and the Moon. And people always this is actually quite accurate in relative. People normally have drawings with the Moon quite close to the Earth. This is about 3 days, 300,000 kilometers. And this is the famous Earthrise image taken, I think, Apollo 8 from the Moon back to Earth. If I take the same picture from Mars, this is a picture from the Curiosity rover looking back at Earth, you've got 1 pixel. That is Earth. Now that distance, Earth to Mars, is 1,000 times roughly from Earth to the Moon. So it's a huge distance. It would take months to get there, 3 months up to a year maybe. So whatever we're going to take is going to be highly expensive. So whatever we take, we'll need to pack light and compact. That's the idea. So let's take as little as possible and let's recycle and upcycle as much as we can. The other great thing about Earth, of course, is magnetic poles, which means it deflects and it protects yourself from radiation, from really harmful radiation that comes from the sun, but also from the cosmos. On Mars, that doesn't happen. So all the radiation really hits that surface. So we need to protect our astronauts from that. Now, radiation protection, that's a really important one. What else is there? Well, it's a very barren landscape. This is a picture that Curiosity rover took from Mars. 1/3 of the gravity, right? So we'll all feel 3 times lighter, which is kind of great for architects because we can make stuff a little bit thinner. We love that. The atmosphere is mainly CO2. It's much thinner atmosphere as well. It's pretty cold, -70 most of the time. And what else do we have? Well, not much. Regolith, just dust, lots of Mars regolith. And so for us to then protect our astronauts, let's see if this works. This kind of works. The best way to protect our astronauts is really to go into a cave. That would be the best thing, right? Go into a deep cave where you have a lot of mass around you. We're not going to do that because we don't know where the caves are. We don't know if there are any. So our idea is a shell structure on the outside that is made out of 3D printed regolith. And on the inside, we have these pods, these kind of unfolding inflatable pods that would actually protect our astronauts and actually give them an atmosphere, so a breathable atmosphere. So there's a pressurized element inside. These parts are made on Earth and are highly engineered and fabricated. The outside part is just a shield against radiation, will be done on Mars. The way we're going to do this is by an army of small robotic printers. Because, of course, if we're going to build this big shell structure, we're going to live underneath. We're not going to do a traditional printer where we need a big machine. I just said we need to pack light. So to pack light, and we're going to bring a whole set of small robotic devices. And here they are. right? You have 4 different types. We have one that goes and scouts for the regolith, one that digs it up, one that transports it, and ones that will print it. And we'll be using microwave technology to kind of like fuse the regolith layer by layer. This is one of the first images that we had from our visualizer, and we love these images. But one thing she did was kind of clever and interesting, I thought. In the view, she put all these kind of robotic devices that just finished printing our shell structure and put them on a heap there. So really, I just created the first boneyard of robotic devices on Mars. Not a great thing to do, right? You know, the first thing I do is kind of make a mess. So we were thinking, that's not great. Let's go back to the drawing board and let's see if we can design something which is better. And we came up with this. It's a modular system of robotic 3D printing system with modules, and they can reconfigure themselves into different types of robotics. So we've got our little video here. We've got our little rover, the scouter, but when we then add some more wheels to it and some diggers, these diggers actually kind of developed by NASA, this type of diggers. We have a digger, and then we can add our printing devices as well. Now these things, you know, are still conceptual. We haven't actually built them yet. We are working on a research project where we're building some of these, and then that's our printing process. A little bit showing how they actually would all connect and how they could reconfigure themselves. And yeah, another little video, our little scouter. I always get lots of comments that a one-wheel scouter is not a great idea because it can't turn around the corner, which is true. But we might redesign that one. The digger that digs itself. Okay, interesting thing about diggers is because you have, why this digger looks like this is because on Mars you have 1/3 of gravity. So these actually kind of are these round cylinders that dig themselves into the Martian regolith. So that way you don't need mass to actually dig regolith, which you normally do on Earth. You have big machines and they're heavy for a reason. Here they don't actually need to be heavy because they actually kind of counter-rotate themselves into the regolith. So and then that printing process where we get the regolith delivered and through a microwave process, layer by layer gets printed. So then to the habitat itself. So we have this 3D printed shell structure. Underneath we have 6 inflatable pods, and we have these kind of 6 connector pods that actually allow access to the outside as well. Regolith, 3D printed regolith is a bit like really bad concrete without rebars in. So we designed it in such a way that it would be a pressure compression only structure, right? So we used Karamba and Kangaroo to kind of do that. We worked together with Eckersley O'Callaghan engineers on this. So we knew there's no bending moment, a very little bending moment or tension within these structures. Then underneath we have the inflatables. We have the smaller connector pods and then the larger ones inflating up, kind of unfolding and inflating. And now you might think, you know, the inflating architecture, that's a bit sci-fi on Mars. Well, not really. And for all the things, all the technology that we use in this project, we're actually using tech that has already been researched. So it's not sci-fi. We call it sci-fact. This is 1960s, 1968, I think, where NASA is with Goodyear prototyping an inflatable space station, right? So people have been thinking about these things for a long time. This is TransHab in the 90s was NASA was developing an inflatable space station. Why inflatable? Because you can compact it much better. You can have, like I said, travel light, but travel compact as well. So you could actually kind of fold these things up, get them into orbit, get them to Mars, and then wherever they are, they can expand to much larger spaces. There is actually an inflatable habitat at the moment. This is Bigelow. Unfortunately, the company went bust, but there is at the moment at the ISS, there is an inflatable module. This is the inflation process. This is an astronaut doing some testing within that. It's just a prototype within that module. but it's something that's becoming quite real. This is Sierra Space. We're working with them as well at the moment, and that is them testing out a one-to-one inflatable space habitat. So this will be the next generation of space habitats that will replace the current ISS in probably about 5 years' time. We said that's quite critical of what has come before. This is the Columbus module in the ISS, and if you look at it from a pure architectural perspective, so there are cylinder volumes because there are pressure vessels. So it's great to have curved shapes. And this is also the maximum amount of volume that fitted into the space shuttle. How they are fitted out? Well, they're fitted out by these kind of racks, these science racks you see on the left-hand side and on the right-hand side. And then we have storage on top and bottom. So in a way, the ISS is just a whole lot of corridors. That's how it actually kind of designed. So we also feel that we know that certain of these racks, these science racks, just need to be set up and left alone for maybe weeks sometimes. So the space in front of it is actually not that usable. So we actually think that the ISS is maybe from a space perspective, spatial usability perspective, not that great. So we're looking at things like this, very simple solutions. This is a rack system in a library. Really, it saves a lot of space. And we kind of took that simple architectural idea into our design. So we have a rack system as well, a movable rack system on rails, but it's in a radial system. So you see each pod that you see here has a different function. There's a living one, there's a greenhouse, there's a lab, there's the bedroom one. They all organized in the same way. They're interchangeable modules. So if I want to, at some point, make my lab into a greenhouse, I can actually swap that around, or I make a half a greenhouse, half a lab, I can do that as well. And these things are actually on racks, so they kind of move about and are much more. So this is our lab, our astronaut, which is actually Chris, our visualizer, is setting up an experiment. Once he's done that, he can actually open up another section of it and close this one off. So, and we do it for everything. Also for our greenhouse, for example, and for our living spaces. Now, one thing we wanted to kind of start thinking about is recycling and upcycling a little bit more. And we also started to think about what would our astronauts wear? Because there's quite a bit of fabric that is not really used. These are landing parachutes on Mars. This is the Perseverance rover when it was landing on Mars, taking a little look back at the chute that was dropping it on Mars. So we just kind of started to think, like, what if we can make clothes out of this material? And then we knew somebody that actually does that. This is Chris Rayburn, a fashion designer in London. He has this Rayburn lab in Hackney. He's also creative director at Timberland. But he's been doing this for years. He actually makes materials out of waste material or surplus materials, out of parachutes that are not being used anymore. The jacket I'm wearing today is actually made out of Chinese parachutes. That's one of their designs. And we thought it was a fantastic idea. And that idea of recycling and upcycling, once you're there, we think is really, really important. This is our little green screen shoot in the office. And there we have, this is Chi, our astronaut or interior designer from the studio, is now an astronaut fixing something in our workshop. And you see sewing machine there, making some new clothes, but also some big Delta 3D printer here, doing something over there. So I said, pack light, pack compact. This chaise longue is not exactly light and compact, of course, but I didn't bring it to Mars. It's actually 3D printed there. So we started to think, what parts could be 3D printed? Why don't we use plastics, waste plastics, because there will be waste plastics on the Mars base as well, from food packaging, for example, or from experiments, and use this to 3D print. We collaborate with that then with Nagami, a 3D printing company here in Spain and in Avila, outside Madrid. And so we worked with them on this chaise longue, and this was indeed printed from recycled plastics. I think from medical plastics, really. So just to imagine what it would look like, what it would be like to live on Mars and actually having to 3D print your own furniture from your waste. And this is the kind of the chair. Now, one of the things that we found important, of course, is protecting our astronauts. I explained it already. But the other thing is that view out, right? Remember Skylab, how we didn't have a view out? We think it's really important to have that view out. But at the same time, we need to protect the astronauts. Now, this is the cupola, it's the most famous place on the ISS. The way they protect the astronauts there is with these massive mechanical flaps, right? It's a very engineering solution, right? To kind of have a thing, we need to protect them, so we'll have something that closes it up. We thought it slightly differently for our base. We went to, again, an architecture example, a Mediterranean courtyard, right? Because what's great about these things is they let in indirect light. You actually get a view across the habitat as well, and you stop direct light hitting your habitats. Well, and in Mars, we did kind of the same. So our Mars project here has this kind of centralized courtyard, really, which gives us views out and also views to the rest of the base, but actually also stops radiation hitting our astronauts, because the solar radiation, the radiation from the sun, was actually the harshest one. And yes, we had to trick our solar analysis software a little bit to make sure it's on Mars. But we did some analysis then again to kind of see that, yes, are our astronauts ever being hit by this radiation? And here you see that the habitat itself, the little physical model that we made. You see the modularity of these modules as well. As I said, it's not sci-fi, it's sci-fact. So on the right-hand side, you see the architecture. There's a drawing we did for when we exhibited at the Design Museum. But on the left-hand side is the mission architecture. So we worked with students from Cranfield University who, instead of making beautiful drawings, they actually had loads of spreadsheets, connected spreadsheets, to kind of calculate how much it would cost us, what the weights would be, what the maximum weights would be, how many kind of launches we would need, how many kind of transfers to Mars we would need, how long everything would take. So they had all these spreadsheets, and we worked with them. They're kind of systems engineering students from Cranfield. This is the team here, and they helped us actually keeping track of everything, right? So, and at the same time, what we also do, we actually get a lot of engineers and scientists in. So this is us midway through the design process, doing a design crit with having roboticists, mining experts. This guy in the front here is a Mars meteorologist. So space psychologists, space anthropologists. So everybody was in the room, and that was actually fantastic. And we gave them all a red pen, and they could comment on our design. And there was something for them quite weird to do, because they used to just kind of look at peer review papers, right? Not being thrown into a design process, but they found it really refreshing. And the fantastic thing was how all these scientists were kind of all the time disagreeing with each other, which I found absolutely amazing. But it was really, really helpful to kind of make actually quite big changes throughout the design. We're really lucky that in the end, we were then invited by Design Museum to actually build one of those. So we went back to Manuel at Nagame, said, we need more of these prints. We built actually an inflatable, and we had this big screen that we then virtually could see that view out from our Mars habitat. And we even made the rack that we were able to move. So we make it's a slightly smaller one. The original one was about a 9-meter diameter. This is about a 7-meter diameter part of that habitat. But people that could come to the Design Museum were able to kind of experience it as the real thing. And you see a little bit more of that. Now, next thing was I'm going to talk about 3D printing through the Norman Foster Foundation atelier that we've done. And we're kind of, with Manuel and his 3D printing furniture, we were kind of really intrigued by it, but we wanted to kind of push it to the next step. What we wanted to do was do it for real buildings. So our proposal at the robotic atelier was, we got about 10 students from around the world coming to there, and we were able to work with them. We said, like, take a classic facade system, right? Because facades are interesting things because they're actually quite complex. They have different materials to do different things. Let's take 3D printing, not concrete printing that I've done in the beginning of my career, but like take plastic printing, recycle plastics, and see what we could do, what we could come up with. And again, it was me and Manuel working there for a week, and it was actually really fantastic because we were able to we're just scratching the surface, I think, but really starting to investigate what it could look different and how one material could suddenly have different functionalities. Could it, capture water? Could it become, different insulation capabilities, different ways of stacking it, different ways of having rain screens and so forth. So, but it was kind of, it was 4 days only, but I think all this stuff that you see there printed was only designed and printed within 4 days. So it was quite an intense few days, but it gave us the idea to kind of push that further. And then I met a client who wanted to push it further. This is on the right side. This is NAC from the TO Foundation in Switzerland. And he was really keen on that idea of taking recycled plastics and starting to build with it. He was interested in kind of doing it in 2 different locations, which I found really interesting because I thought, well, with 3D printing, we can adapt ourselves to different climates. There was one really hot one, which is Senegal, and another one in Switzerland on a glacier. The idea was to just design a meeting space. That was it, right? So it's a simple pavilion, but not just a pavilion. It was actually kind of, it's a tiny building. It has to be able to operate as a building. And we looked at a lot of indigenous structures because what we love about those is that they really are adapted through their materiality, through their geometry, through the way they're actually built, through their direct environment. Now, we want to do the same thing. So could we design these pods that they might be slightly different, that they adapt themselves really well to their climatic conditions? Maybe it's the skin, maybe it's the structure inside that is slightly different for different locations. So the first one was La Crosse in Senegal. And for that one, we decided to have this pod with lots of cross ventilation because it's really hot, but at night it actually gets quite cold. So that really works. And we had fins that actually start shading the building. Simple idea. So self-shading, as particularly in the locations where we have actually more sun. And again, some analysis, continuously doing analysis as well to make sure what we do makes sense. This is solar analysis of the one in Senegal. We figured out it wasn't actually enough, so we had to, something happening with my fonts there. We had to make sure that so the building wasn't cold enough. So we worked with Transolar climate engineers here, and they said use mass of water in the building. So that would actually then cool down at night and would radiate during the day into the building. So we tried to do that. We actually we're quite literal. We were starting to think of why wouldn't we use recycled plastic bottles that we somehow squeeze into the structure and able to kind of cool it like that. At that point, we left the design at that stage. Oh no, actually we started to do some prototypes already at Nagami. You see here, we use kind of the big fins actually shading the building, the self-shading, very thin because we want to have as little mass as possible that it actually don't heat up. And here's actually starting to kind of pull some of these parts together because they had to be done in parts. These are some of the renderings that we've done on for that project. At that point, we left it at that stage because we then looking at a different location as a location in a cold climate. And Glacier 3000, it's a glacier above Stad in Switzerland, very cold on a glacier. So we need to adapt the same pod in a different way. So there's no cross ventilation anymore. And we thought, let's adapt ourselves to the environment. Let's use snow to actually start insulating the building. And yes, you can actually insulate a building with snow. Snow actually works quite well. Particularly fresh snow works well as an insulator. So we wanted to see, can we adapt that skin to not just shade from the sun now, but it suddenly starts to be something different and actually start to capture snow. And that's kind of what we came to. So there's all these fins now are shorter and they stick out. they want to capture the snow for our to help with insulating the pod. Again, here we don't have cross ventilation anymore. It has a door, it has a cupola, so, and it has much more insulation, and so we start to kind of adapt it slightly for this new climate. New material, I had to then work a lot with structural engineers to kind of see what that material actually behaved like, start to calculate Young's modulus and all that, because it was all very, very new. You know, it was all quite experimental. The whole pavilion, you know, as I said, would be in parts. It would not be just printed in one go. So we have about 24 different parts. We're now looking at an internal structure, an external skin for a rain screen and for climate conditions, and an internal skin for the interior. And here you see the snow kind of being captured on the pod to help with insulating. And these are actually some new images. We're actually going to, hopefully you'll see this in the zine as a little preview here. You should see this in the zine in about a week's time, I hope, or in the press, in further press. 3D printing pods. Now I think this is my last project. Still looking a bit of the time. Yeah, I'm doing okay. Different location. Same client, actually. We're still working with TO organization on this one. This is Northern Uganda. In the largest refugee camp, or the second largest refugee settlement in the world. 270,000 people live there. This is not, if you think, people think refugee camp, refugee settlement, they think like tents from the UN in a big grid. It's not like that. This is quite a large area where refugees from southern Sudan came, and they've actually started to build their own houses in the location. We were asked by the TO Foundation to actually build a music center, an art center, because there is no cultural center. Imagine 270,000 people living there, but there is no cultural center. There is no cultural buildings. And think about placemaking in cities. Cultural buildings are often the center of cities. So it would be a really good thing to do. And we're working, the TO Foundation is a client, but actually our real client is Sine Locata. And that's a local refugee-founded organization that actually teaches the refugees two things. They teach music and dance, and they also teach computer skills. And for both of them, they also teach them entrepreneurship, because they want people to, by those two things, actually starting their own jobs, because there are no jobs. They're in a refugee camp, you know. So for that reason, we're really excited to actually work on a project like this. So this is some of the pictures of Bidi. You might think it's quite spread out, but actually it's quite a dense place, because also kind of imagine, you know, there is no sanitation, there's almost no running water, there's no electricity whatsoever. So it's a tough place to live in, and it's also a tough place to build something new. This is the family of Maui. Maui is the guy that we working for that will be operating the center. He's from the Sine Locata organization. That's his family that lives just down the road. So me going there in September was really an eye opener, because I always had Maui on the calls, and then when I saw where he lived and meeting his family was so great. This is the center. It's an elliptical building for a few reasons, actually. And sorry, this is the kind of the site. So this is the huge site of Bidi in Northern Uganda, and we're just located just on the bottom there. This is the street that we're just off, and there's a big tree on the side as well, which we really liked. And this is the site. It's a little model of what we have. The big tree here. This is Sine Locata in the current buildings. This is the main road. And a really important thing on the side is this borehole. Lots of people are coming to the borehole and see the roads all leading to the borehole. And that is where people come and get water. Water is very carbonated there. That comes at that borehole. So one of the things we thought of, like, let's try to kind of help with that as well. Let's try to help with the arts. So the building has two centers. It has it's an ellipse. Ellipse always have mathematically two centers. One center is really the performance space and the auditorium, and the other center here is really where we collect the water, because the whole roof actually will work as a rainwater collection. Besides the auditorium, we also have a classroom here, music classroom, and a recording studio. So thinking more about entrepreneurship, not only knowing how to music, but recording music and maybe publishing music. So there's that small little teaching space. And we also want to make sure the building never outgrows itself, right? So we're kind of opening up the back of the building so the stage can become much bigger. A lot of bigger audiences can come and see when we open up the building. Like I said, we kind of looked a lot at different roofs. In the beginning, some of our sketches here, but we settled on this roof. And as I just kind of mentioned before, the roof really is a big funnel. It's a massive funnel that collects all the rainwater to the middle of the building. And besides the music and dance being celebrated, collecting water is celebrated as well. It's a central part of the experience of being in that building. When it rains, you will see the water being flowing into this kind of central part. The water then gets collected to tanks just outside the building and then distributed with near the main road. So people, when the site is closed, they can always get the fresh water. Doing some analysis again on how the water actually flow to the inside. But also again using technology, using some solar analysis to see, because we're near the equator, so solar analysis looks slightly different there, to see that it would actually shade the building. One thing we also kind of recognize that the building is on quite a slope, and there are quite winds. Definitely from the south. There's quite a lot of southern winds that we have, some analysis that we did. And for that reason, we decided to actually kind of lift up the roof quite a bit. We made a very thin metal roof. There's no insulation in there. And we get the wind there just to kind of cool down the building. We let it heat up, but it can cool down quite quickly as well. One of the questions we often get is that what happens when it rains? Because it's going to be like a drum. You're going to hear it really, really loud. But then we spoke to Maui and the people from Senior Locator, and they said, like, oh yeah, when it rains, yeah, we just stop the performance for a little bit. It only rains like really hard for about 10 minutes or maybe 20 minutes. And then, yeah, it's just like, oh, in a classroom, we just stop the classroom a little bit. So we thought like, okay, so we just kind of manage it that way. And we just kind of suddenly we're like, okay, yeah, let's not worry about that. What is more worry is actually being able to kind of cool down the building without doing any mechanical system. So it's just passively ventilated. Quite a complex roof. And for that, I kind of start to use all my the skills I had when I was working at Foster's by being able to bring really complex shaped buildings into quite a simple fabrication system. So here as well, we know the roof could only be built out of straight bits of metal. So we made this kind of quite complex shaped curve. We flat panelized it, and everything is made out of simple corrugated metal panels, which are locally available. The setting out, another cool thing about the setting out is an ellipse. You might think, oh, very complex to kind of set out on site. Well, not really. If you have an ellipse, you can set out by 2 pins and a bit of string, because that is actually the definition of an ellipse, that each point, the distance of it to the 2 center points, the sum of that is always the same. So actually setting out the building, a very complex build, becomes really easy. But we need local help, of course. So we work with a company called Local Works, Felix Holland, who has a company there for over 15 years. And the first thing we did, we asked him is actually go to the site and actually start to understand how the local building techniques are, but also understanding from his building techniques, because he's been building in Uganda for about 15 years. So one of the things we learned from him was the bricks. And to use SSBs is solidified soil bricks. So not fired bricks, because the problem is around the camp, there's no wood anymore, right? So we're not going to use the wood to kind of fire the bricks. What we're going to do is we're going to compress them, all right? And this is bricks used with soil, local soil, with then a little bit of cement and lime in there, and we're pressing these. So 50,000 of these need to be made. The great thing is we also use local people to make them, right? So so that's a kind of a great way to kind of get the local people involved at the same time. And we use these bricks, and I was just talking to Arete about it. I said, like, we're using bricks, so it's not really additive manufacturing, but really, I think in a way it is, because you kind of layer by layer do something. And we're not just going to use these bricks to just make walls. We use them we make openings to ventilate the building. But we also start to do this where we create a layer of diffusion for the acoustics for the classroom. And for the recording studio, we even go further. We have diffusion, but we also have absorption. So we use something what's called a Helmholtz resonator. So we have actually a cavity in the wall that with particular distances that will fill up with material that actually kind of absorb the sound as well, particularly in the recording studio. Normally it's done with very high-tech materials, but we think by just using the geometry of these bricks in a particular way, which you do with 3D printing as well. You know, you start to use geometry in a particular way to get certain functionality out. We're doing the same thing here. This is me and Maui and Victor from Cinelocator using our HoloLens to kind of show them what the building will look like in hopefully, well, it will be less than a year and it will be finished. And this is us in with Felix and his team in Kampala looking at the mock-up, right? Really interesting thing is we worked with a local architect, of course, with local works, but now they're also the contractor, and that's fantastic. I think it's a little bit like Studio Mumbai, where they often are architects and contractors. So Felix is becoming like the Ugandan version of Studio Mumbai, and this is even before we actually selected them as a contractor. So they already were building stuff with the real materials in Kampala, and just going there and testing it and checking everything out. And yeah, so this in September, hopefully, might be October, November, but this will be there in Bidi. And to be honest, it's one of the most important projects I think I've ever worked in, because I'm really going to affect an area and people that I know now personally, hopefully in a really positive way. So yeah, I'll leave it at that. 4 projects in very different locations in very extreme environments. Thank you.